Today we're going to talk about Chapter 5, Section 2 of our chemistry book, where we relate the Bohr model with the emission spectrum, and we also talk a little bit about orbitals and how those affect frequencies and photons and light of the electromagnetic spectrum. So first we're going to go over a few vocabulary words and look at how the Bohr model relates to those vocabulary words. So the first thing we want to look at is this is a Bohr model, a typical Bohr model. It has a nucleus that contains protons and neutrons. The electrons, according to Bohr, are in specific energy levels that are rotating or revolving around the nucleus, similar to how the planets revolve around the sun. This is not an exactly correct model, but it does help us in this portion of learning about electromagnetic radiation. So we're going to use it, but then we're going to talk about how it's incorrect. So the first part we're going to do is look at how electrons actually exist inside of energy levels. If an electron has low energy, it's going to be in an energy level closest to the nucleus. But as it gains more and more and more energy, or more electrons are added to the atom, then they are able to exist inside of higher energy levels, further and further away from the nucleus. So what happens is when an electron absorbs energy, it will jump from a low level to a high level, so it'll get further from the nucleus. This higher level that it exists in is called an excited state because it absorbed energy in order to get to that state. However, that state is not stable, just like if you drank 4 or 5 or 6 Starbucks coffees or had a bunch of Skittles or some sugar or something like that. That's not a stable state. You have a lot of energy, but then you have to come down or you'll crash from that. So the electrons do the same thing. When they go back to their original state, then this is called the ground states, where they normally would exist. When they come back down from the excited to the ground state, then they emit energy known as electromagnetic radiation. Sometimes, if that EMR or electromagnetic radiation is within a certain wavelength or frequency, we get to see that as visible light. And that's exciting because these are the kinds of things that are used in fireworks so that we can see those different colors of light. So Max Planck is the one who said that light doesn't only act like energy, because energy has wavelengths and waves and frequencies. He said light also behaves like matter because it actually has carries packets of energy called photons. When we draw the photons, we use a squiggly line like this. This is an example of a photon or a model of a photon being given off by an electron. And so we use the squiggly lines, and that each of these squiggly lines represent a packet of energy or a quantum of energy. So we'll be looking at that. Now in the class, we looked through spectroscopes, and a spectroscope is simply a fancy prism. Inside of this little black box is a prism. And what the prism does is it bends the wavelength of light at different angles so that we can actually see the different wavelengths of light. It's sort of like splitting it into its different parts. So when we have a regular white light, like the sun, for example, our spectrum is going to look like a continuum of colors. And so it's all your Roy G. Biv colors from the rainbow, but really they come from the electromagnetic spectrum. So when you color this part, it's going to be just a constant flow of colors into each other: red, orange, yellow, green, blue, and violet or purple. And so it's going to have the whole spectrum of colors. However, if you observe light from hot gases, where we have taken electricity or fire, depending on what we're doing, like fireworks, you do that, and in the lab we'll do that. But if you take those hot gases and you look at them through a prism like we did in class, again, the prism splits the different wavelengths of energy being given off, and so you can specifically see the bands of energy. Now, these bands are like fingerprints. Every single element will emit a different set of wavelengths of energy, and so you'll get a different set of bands of light. This is called an emission spectrum. So each element kind of has its own unique emission spectrum. For hydrogen, for example, you get to see two violet lines, a blue line, a green line, and a red line. And they're at specific wavelengths. And in your spectroscope, you have numbers under here. And so those numbers represent the wavelengths. So what this is saying is that the colors, when you excited an electron and it went from a ground state up to an excited state and then fell back down, when it fell back down to that ground state, it emitted a certain color. That color is going to be represented when you look at the prism. The prism allows us to see that color. So the color here is corresponding to the color here, or a certain wavelength or a certain frequency. Notice that when an electron falls a very short distance, you're going to see a longer wavelength, and that longer wavelength corresponds to the red region of the electromagnetic spectrum. But then if the electron jumps to an excited state and has more energy, like this one jumped from 2 to 4, and when it fell back down, it gave off a photon of energy. Well, now it's a higher energy and shorter wavelength, and so you get more of a green color. And then you could have a yellow color, an orange color, and so forth. And so as you fall further and further, more and more states, you give off more energy, and the energy, low energy is here, and higher energy is in this region. So hopefully these colors and the Bohr model connect to each other, and it makes sense. So what we're going to do is we're going to actually do one by heart. This is the hydrogen atom, and so it's just an example of one. Not every single atom is the same. And so in a hydrogen atom, if an electron jumps, it only has one electron, and when it jumps from the second to the third, because we add energy to it with electricity, we don't see anything. But when it falls back down from the third to the second, it will emit a certain wavelength of energy, and so we see that in the form of a red wave. So, and again, this chart will show that, like, if it jumps higher, you'll get a different wavelength. If it jumps even higher and then falls back down, it'll emit a different wavelength, and so forth. So if you look at this Bohr model again, the shorter falls correspond to the red colors in the hydrogen atom. And then if it gets excited even more, we don't see anything, but as it falls back down to it from the excited state to the ground state, and again, depending on where that electron normally is, it's going to emit a different wavelength of energy. And these photons that we're drawing with squiggly lines are packets of energy. And so these are photons, and they're represented by these squiggly lines, okay? Each atom is very unique in how this Bohr model will look for that particular atom. This is the Bohr model for hydrogen and how hydrogen would look, but there are other atoms, and so helium or argon or fluorine or nitrogen or any of those would look different than this. Still the same idea where you're jumping levels, and then when you fall back down you get colors, but not exactly in this particular color with these particular levels. And the reason they're different is because each atom has a different number of electrons. Hydrogen just has one electron, so he's doing all the jumping, but other atoms have maybe 4 or 5 or 10 or 86 electrons. It just depends on the atom. So all those electrons have some options as to jumping up and down levels. Also, the higher you get in the periodic table, you have a lot more protons in the middle. And so these electrons and these protons are attracting each other. And so the distance between these different levels are different for each atom. And so they're going to look a little different. I want to point out that these levels we've been talking about here are numbered by quantum numbers. There's 4 different quantum numbers, but the principal or the main quantum number for each energy level is noted by an N, and it's simply just numbered further and further away from the nucleus. And so this is the first level, so it's N is 1, that's its principal quantum number. N is 2 is a principal quantum number, and so forth. So let's move on to orbitals. The Bohr model is wrong. And makes you think that they're perfect little concentric circles, but that's not actually what it's like in reality. I encourage you to go to this website and watch this very, very short video. It explains this, and it's an animation that kind of explains how this works. So electrons don't live in just circles. They actually, the clouds that they live in are different shapes than circles. And so the shapes of the clouds are spheres. There's a P shape, which is dumbbell or a pear, kind of pear-shaped. That's these right here. There's a D shape, which I call daisy because it kind of helps, it sort of looks similar to a daisy, not exactly. And then the F shape is very funky. So the four shapes that electron clouds can be are S, P, D, and F. Those are the shapes of the electron clouds. In the first 7 levels, they all have S orbitals. So there's a 1s, a 2s, a 3s, a 4s, a 5s, and so forth. In levels 2 through 7, they're going to have these 3 p orbitals. So there's going to be a 2p, a 2p, a 2p, 3p, 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 4p, 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 and so forth. In levels 3 through 6, they all have these d orbitals, or these clouds. And so when you get into that outer level, the 3rd level, it's also going to have all these d's. Each of these orbitals holds exactly 2 electrons. So 2 here, 2 here, 2 here, 2 here, 2 here, and so forth. So they can all hold 2 electrons. Levels 4 and 5 also have those f orbitals. We don't have a diagram of those, but that's okay. That'll come later. All of this is going to be used in our next unit of electron configuration. So it's important to be familiar with these orbitals, that it does not look like the Bohr atom like this shows. The Bohr model shows that as you add energy to an electron, it'll jump from its ground state to its excited state, and that's then it'll fall back down, and when it falls is when you see the photon of energy. What really happens in the atom is that you start with an s orbital, so like the first 2 electrons are going to be in sort of a cloud type shape, but then the next 2 electrons are also going to be in a cloud, but it's larger than the first cloud. But then the next 2 electrons are going to be sort of in a P shape or a dumbbell shape, and then the next 2 electrons can fit this, or actually 1, and then they go back and fill each other up. Then the next electrons are added into this shape, and then you have another S and another set of P's, but this is what the D's would look like, and so forth. And you can kind of start seeing how it gets more and more and more complicated, because all of these different shapes start, as the more and more electrons that you add, these shapes start adding up and compiling. And so it does not look like this beautiful concentric ring arrangement like Bohr said. It's a lot more complicated in that you have sphere shapes and pear shapes and daisy shapes and funky shapes and so forth. And all of these shapes represent where the electrons are going to exist. So I just wanted to point that out. All right, well, good luck on the rest of your assignment.